welcome Mindsetters to Learn Extra Live Maths with E.T. How are you, E.T.?
I'm all right, how are you?
Great, thank you.
And greetings to our viewers out there.
Yes, of course. Greetings to you guys. What are we doing today?
Linear programming, another tool for optimizing our resources.
Okay, that would be
The
awesome.
use
Thank
of our
you, E.T.
resources.
Thank
Great.
you.
All right.
So guys, as you heard, we're doing linear programming, and make sure that you join us for some awesome fun, because linear programming is a great way to get marks in your exams. You can ask any questions that you need to ask us on facebook.com/learnextra, as well as on our Twitter page @LearnExtra. And of course, today we have some awesome prizes to give away. We have this Casio camera. I know it's awesome. I know it's also awesome to look at. So make sure that you get this for yourself. Also, calculator and the Casio labeler. So today these go out to the best mindsetter, guys. Make sure that you are all over the page today, because it is going to be so exciting. And thank you to Liberty for bringing us such an awesome show where we can actually reach out and help you grade 11s. And I know that because you're in grade 11, you're stressing about matric and these marks that you need to get. So make sure that you ask us anything that you need to ask us. Exams are soon, guys. Don't take that for granted. That's why we had to help you. Over to you, E.T.
Thank you, Kathleen. Today we're doing linear programming. And let me start off by saying all of us have an objective to satisfy our needs or our desires, or to perform certain functions. And in the whole scheme of things, we are going to look at what resources do we have that we can use to achieve all of those objectives. And linear programming therefore becomes a tool that we can use to optimize the use of our resources. I've defined it here as a decision-making tool. Where's my pen? All right. So I've defined it as a decision-making tool about our ever-limited resources. The kind of resources that we have is typically money, time, space, and the quantities that you can accommodate in space and all those kind of things. Now, if you look at money, or all of these resources that we have, if you have money, you want to spend it on items of type A or type B or type C, but we limit, for this grade, we limit it to 2 items. Let's say type A and type B. So you want to use your money, let's say, on buying some sweets or some biscuits. We limit it to only 2. There could be other things that you want to buy. And when it comes to time, for instance, say after school, you realize that you've got about 6 hours that you can allocate to, let's say, playing tennis, and the other one for finishing your homework. And those are now 2 items given. Let's say you gave yourself 6 hours, in the afternoon to use for those 2. And that is time. When it comes to space, for instance, let's say you've got 1,000 square meters. You want to build a house. You want to also have space for your kids, some playground for your kids. And also maybe say a garage for your cars and all that. All right. And when it comes to numbers that you can accommodate, you've got a restaurant, let's say, and you want to know if you've got waiters and guests, how should you balance the numbers? It's all about balancing our desires, our needs, and, in the end, achieving our objective. All right, so if you pick type A and type B as the items that you are going to use your resources on, we will have to quantify the type A and the type B. And usually we use the X, the Y, and it could be the Z as well. So those are the variables that we use in quantifying our resources. All right, so I did talk about our resources being limited, always limited. And there is a term that I want to introduce there to suggest limit. To suggest that our resources are limited, we use the word called constraint. So you'll come across this word several times. So our constraints are going to be linear. We're going to use linear constraints, and linear constraints will come in the form of either ax plus by equal to c. There are three forms of the linear equation that you can come across. It will be ax plus by equal to c, for instance, y equal to mx plus c. This one I'm sure you're most familiar with. You could have another one that says, okay, let me just rewrite this, x over a plus y over b equals to 1. All right. So those are the three types of linear equations that you can come across when we talk about our linear constraints. All right. Now the question is, how do we represent these things as constraints? You now are going to bring in what you call inequalities. In your equations, these are equations. So basically you will start using symbols such as greater than. I'll just extend my page there. So greater than, another one would be less than. Another one that you're going to come across will be greater than or equal to. And the other one is less than or equal to. Those are the inequality symbols that you're going to come across. And those are suggesting that you have something less. You don't have more than, let's say, 100 Rand to spend on what you want to spend, for instance. That's what I meant by constraints. The types of constraints that, if I can give them names, will be those that are expressed. In other words, they are given to you. All right? They are given to you. For instance, you could have, let's take y greater than mx plus c. So that's what we mean by linear inequalities. And that could be one of the way of expressing your constraint. Right? So those ones are expressed when they are like that. These are explicit. They are given. You can also say explicit. So those ones are basically given to you. Maybe just to run quickly through the kind of information that you can come across. The information that will be given to you, and the task will be to convert information from one form to the other. You will either be given information in the form of, as a set of equations, for instance. You will be given information as a set of word statements. And you can be given information as a table of values, for instance. And you can also be given a graph, graphical information. That's a pictorial information now. And you can also be given a set of points that you can plot. And each of these things can be converted from one form to the other. And that's really where you will be tested. Okay, in this case, I'm giving you an equation, for instance. I call this an explicit constraint. An implicit constraint typically will be to say, well, if I'm going to buy sweets and I'm going to buy biscuits, there's no way I'm going to buy negative sweets. There can't be a negative quantity that I buy. And as a result, you say, let's say you've got X and Y. So you'll be saying X must definitely be greater than, or it could be 0. Okay. Either you buy nothing, or you buy a positive quantity. And you could also have Y greater than or equal to 0. Okay, so those are unexpressed. So I don't have to tell you. If I say to you A is greater than B, you can conclude that B is therefore less than A. So the same with this thing. So those are implicit. You have to know them. All right. Right. Katleho, are there any questions up to so far?
There are no questions so far. You can carry on.
Oh, we're going smooth.
Yes.
Thank you.
Okay. No, that's fine, guys. Please ask any questions that you need to find because of the fact that we are here to answer them. So right now I'm looking at the page and I love seeing questions on the page so that you know that I'm here for you. And that's why I'm replying, because I am here for you. E.T., are you ready?
Yes. Okay. Let me create a space for myself.
Okay.
There. All right. So we've dealt with the different types of constraint. I think the last one I wanted to touch on is the redundant constraint. A constraint that is given to you, but basically they could as well have not mentioned it. Because if I say to you, your value of x must be greater than 10, then again I say to you, your value of x must be greater than 5. It's pointless to say, to give me this second one. Because in any case, all the x, the quantity of x must be greater than 10. Mentioning greater than 5 is pointless. So that's what you call redundant constraints. Redundant constraint. It's pointless. Let me just use the word pointless to mention it. Pointless, or useless, if you want. All right. So if I move on to examples, let's say we take. Let's go to the next. If we pick on, let's say, I did mention the type of information that we can have. Yes, I said you can be given a problem statement, a set of inequalities, graphical information, a table of information, so on. So we are going to learn to convert each of this information from one form to the other. All right? I think what I wanted to go to as well. Right. Okay, one more. All right. We need to recap a bit on how to draw a straight line, because we are going to then relate it to the inequalities. Let's take this equation given here, which says 2x plus 3y equal to 5. The first form that I gave you 3 forms. I've given it in this form. Now, how do you draw a straight line? So you are going to have to find the y-intercept and the x-intercept. That's the quickest one, that I find to be useful. So to find the y-intercept, you are going to let x equal to 0, because then you will get the y value that will correspond, that will cut your y-axis. So that y value in this case becomes, if you divide both sides by 3, it will be 3y equals to 5. You divide that side by 3, that side by 3. Now your y-intercept comes out to be 5 over 3. Then you mark it on your y-axis. What about the x-intercept? To get the x-intercept, you're going to let y equal to 0. If you do that, what do you end up with? You end up with 2x equals to 5, and you divide both sides by 2. Then your x-intercept comes out to be 5 over 2. Then you mark it on your graph. You will be having a graph paper. So in this case, I'm just using a rough sketch. So in this case, you'll have 5 over 2. You just need 2 points. It's good enough to draw a straight line. So then you can join those 2 points. Okay, you can extend it if you want. So that's how we would draw a line of 2x plus 3y equals to 5. Now the question is, if you were given this thing as inequalities, what did you do? In this case, you've been given 2x plus 3y is greater than 5. So you will have to imagine where the line is. In this case, because it says greater than, you would mark anything that is above the line. I use the arrows like that. And for the other one, and notice that because it doesn't say greater or equal to, we actually would be representing it as a dotted line. Okay. If it was saying greater and equal to, that solid line would apply. All right. So this is now representing 2x plus 3y greater than 5. Those arrows. Let me use a different pen to show you when it's less than what it's going to look like. Let's pick that pen there. So if you are given that 2x plus 3y is less than 5, that straight line which you drew for 2x plus 3y equal to 5, you have to mark, let's say with the arrows, all the values that are falling below the graph. All right, so basically that's how you will be showing the inequality. All right, again, the fact that it said less than, and it didn't say less than and equal to, you then have to show this line as dotted because the equal part is not there. All right, let's move on. If we then take, let's take one of the, okay, let's take a few things that are, yeah. Now I'm going to talk about what you call the feasible region, because now that's now an area of possibilities, for where you can find solutions. Okay, where you can find solutions. But I think let's take a quick break.
Okay, Iti.
And we'll come back and start with
Okay,
this.
sure.
All
Guys, we're going to take a really quick break. Get refreshed. Get anything that you need because it does get more awesome from here. And remember, you can always send through any questions from the start of the lesson to the very end of it. I am ready and on the page. See you just now. Welcome back, guys. If you have just joined us, we are doing linear programming in grade 11 mathematics today. It has been awesome so far because you guys are actually getting what's going on. And most of you are saying, wow, yay, linear programming, and that you've been waiting for it for the whole month. So I'm glad that, or not even month, the whole term. So I'm glad that we finally got around to it and you guys are enjoying it and you are understanding it that much more. I know that most of you have come back from holidays, so it's a great refresher for some of you who have already done it. And if that's the case, please send us through with any questions that you need to ask us because we are here to answer them all. Over to you.
Katleho, I think you had a question about real quantities.
Yes, it's a question by Kamogelo.
Yeah.
He asks, how do we know when our information is either real, whole, or integer numbers, so that we must be able to determine whether x is an element of real, whole, or numbers?
All right. Basically, when I define linear programming here, the resources basically, you have to check your quantities can either be counted or measured. It's going to be up to you now to say, can I count temperature? No. You will have to measure it with a thermometer. Can I measure cows, live cows? No, I'm going to have to count them. So really, it's a question of you listening to the kind of information that you have to decide whether it's counted information or measured information. That's my answer to that.
Okay, thank you.
All right. Then we can move to what I was going to do as what you call feasible region. So a feasible region is basically when you draw all your linear constraints in one system of axes, you will come out with lines that intersect each other, but somewhere they will define some kind of polygon. And that polygon could be, if you've got 3 lines, for instance, you expect the polygon that you can define there to be a triangle. And if you've got 4 constraints, what will come out is a quadrilateral, so on and so on. Okay, so then the feasible region is that area where your solution must come from. Okay, and I called it here an area of possibilities. So graphically, like I said, it's the polygon that will come out that where you can find your solutions. All right. So if we can just draw a few graphs, and basically this is now just to illustrate how we can find a feasible region. So I've picked a few that we can draw here. I've got an equation given here that says 2x plus 3y equal to 36, 5x plus 6y less than 60. I've got 4 constraints. We will therefore remember the kind of constraints that we had. Is it explicit? Is it some of them redundant? Do we have implicit constraints and all that? So let's start off with this one. I gave you 3 forms of the equation, of the linear equation. And the one that I'm going to encourage you to use is the last one, which I wrote there. It was saying, let me write it here, x over a plus y over b was equal to 1. So if you have it in this form, which I've given these constraints in, how do you then turn it to that form? Because now this form, the beauty of it is that the a stands for your x-intercept. And the b will tell you immediately what's your y-intercept. This is another way of doing it. So I'm going to say, if I have this equation, for instance, I want the right-hand side of this equation to be equal to 1. Therefore, I have to divide on the right-hand side by 36. So I will say 2x over 36, well, both sides by 36 anyway, plus 3y over 36 must be less than 36 over 36. All right. And what comes out now is 2 goes into 36, 18 times there. 3 goes once, and 12 times there. And there is the one that we've been desiring to get. So now our equation stands like this. It's the same equation, but transformed into the other form of a linear equation. So y over 12 less than 1 in this case. So if you have it in that form, then you read 18 as your x-intercept, like I said, and 12 as your y-intercept. Straight into your graph paper. That's y-axis, x-axis. On the x-axis, you're going to mark 18 as the x-intercept. On the y-axis, you're going to mark 12 as your y-intercept. Very quick. This is the quickest method. You can always look at the equation and say, I know what I had. In fact, earlier on I said let x be equal to 0, let y equal to 0. You can still use that, and it will give you the same answers. So there you are. This is how you draw this. This equation again. In fact, let me deliberately represent this thing as dotted. Okay. So our line will be dotted. And some of you can remember the reason why I would represent it as dotted. Because the sign says less than. It does not say less than and equal to. If it said less than and equal to, I would make it solid. But then, this constraint is not interested in the actual line. This would be for equality, and you would have to show this thing as less than with the arrows like that. Okay, so that's that one. But I want to draw all of these things on the same system of axes. Let me do the second one, and you will do the other two. I will give you the picture, in the next slide, and we proceed from there. All right. So obviously, the second one says 5x plus 6y, and it says less than 60. All right? What do we divide by? We divide by the constant term, which we have placed on the right-hand side of the inequality. So we divide everything by 60. So that's 5x over 60 plus 6y over 60 less than 60 divided by 60. Same story. We desired to have 1 on the right-hand side, and 6 goes once, 6 goes 10 times there. 5 goes once, 5 goes 12 times. So we end up with the form that third form, which is x over 12 plus y over 10 less than 1. So we know we're going to mark 12 and 10 as the x and the y intercept on the same system of axes. So the x, we said x is 12. Somewhere there, we would mark our 12. And the other one was 10. We would mark it on the y-axis. Then we join. Let me use a different color pen. So we would join those 2 points, and that's how our second line would look like. Of course, it must be dotted. Okay. And what do we say? We're saying less than. Less than, again, it suggests that we must have our arrows going below our straight line. So that's where you would have it. What do you notice, therefore? Again, that type of constraint which we discussed earlier on comes up. You've got a redundant constraint. If I already said less than that orange graph, there's no point in going to that purple one and saying less than that, because less than that line, because already this is the limit or the constraint that is of priority, that is taking more priority. All right. So I've drawn those two, and if I continued to do the other ones, you would then come up with a shape that I'm going to show you right now. I've completed this. In the next slide, that's the kind of graph we are going to see. All right, let me extend this. I've just repeated it several times. But for this case, we said, you're going to end up with, if I look at these equations again, I had, what was it? That was our 18 and 12, and the 10, yeah. So we've got 18 for x and 12. Okay, 18, 12, and that will be another 18. Okay, so I'm going to mark it as such. The last one will be a 6. 6, 18, and 12. I'm going to mark it on that graph. 6, 12, and 18. So this, remember, I'm giving you as an exercise. You are going to find out how I got to those values. And on the other hand, for the y-intercepts, we would get, we said here we're going to get 12, 12, and a 10 here, and we're going to get 12, 10, and a 6, and 18 again. 6, 10, 12, and 18. All right, so I'll mark those ones. 6, 10, 12, and 18 would be our 4 y-intercepts. So now this is an exercise for you to go and determine, those values and mark them as such. So each time you deal with one equation or one inequality, mark it and draw immediately so that you don't mix the y-intercepts. And what do you come out with here? The shape of polygon that you get in this case happens to be a triangle. You might say, but you said if you've got 3 constraints, you'll get a triangle, but this time you've got 4 constraints. Why do we still have a triangle? Yes, we're getting a triangle because one of the points, 2 constraints are coming up with the same x-intercept. Remember, the 18 came from the one graph, and the 18 one equation, and 18 came from the other inequality as well. All right, so we end up with that. Now, the feasible region. The feasible region is now this triangle that we have. All our solutions must come from that. We are working within the constraints that we have. We don't have, our resources are limited. So that is the feasible region. And if you were to, for instance, talk about an objective that you want to satisfy, then you have to come with a thing called an objective function. An objective function, again, we use it, we use in straight line functions, okay? Typically, your profit function, your cost function, the quantities that you can accommodate, your revenue function, all of those, we bring them in the form of a linear function, and we call them objective functions. So usually what you want to do with your profit is to maximize it. You want to get the highest profit, given the constraints that you have. And you want to minimize your costs, your expenses. You want to minimize that, which means, you are minimizing. Let me write the 2 terms. The cost, for instance, you want to minimize. You want to minimize your costs if this is your cost function. Now, on this side, you've got profit. You want to maximize profit. Maximize profit. And this is now given as a profit function. All right. So what's going to happen is you're going to have to learn a new concept called, we call it a Sesh Line. So when we optimize, basically we take that objective function and let it translate across your feasible region. Let it translate. It's like someone mentioned what kind of lines? Contour lines or something?
Yes.
So
yes.
those are the kind of, it's more like drawing different parallel lines.
Yes.
Okay. Parallel lines right across your feasible region. Okay. And what you will notice, therefore, if I start with the cost function, let me do this one in particular, extend the page there. All right. So this that we have here says y, we can rearrange it, y equals to minus 6x plus c, let's say. Your cost can range from 0 to any figure that is positive, all right? So you then imagine that that cost in this expression, after rearranging it, that cost is actually your y-intercept. So if you are minimizing, therefore it's like looking for the smallest y-intercept. On the lines that you drew across your feasible region, which one has got the lowest y-intercept? Okay, so what do you say when you use that line across the feasible region is that you are using the Sesh line to optimize whether you are minimizing the cost or maximizing the profit. So in this case, let me use the profit on the other side. I would say y equals to minus x plus p, for instance. Now, the slope of this line will definitely, okay, it could actually be such that you've got lines that are parallel, like that, where you've got profit equal to 0. The next one could be profit equals to some new figure, let's say P1, profit is P3, profit P4, all right? So all those lines are lines of equal profit. So if you pick a point, let's say profit 3, if you pick any value, any combination of x and y, that is inside the region, you will get the same profit. As long as they are on that line, when you substitute into that equation and rearrange to find the profit, you will find that the profit is the same. Okay, this is more like saying 2 plus 2 is equal to 4, 1 plus 3 is equal to 4, 0 plus 4 equals to 4. So those are the combinations of your variables which give you 4 all the time. So that's what I mean by the same profit on the same line. So if you had, I think let's go to an ad break and we can do other examples.
Okay, let's do that.
Right.
So guys, we're going to go for a really quick ad break. During this ad break, please ask anything that you need to ask because there is more after the break. Don't save them till the end of the show. Go through them now so that we can catch them as they come in. See you just now. Welcome back, guys. As you know, linear programming is going to be a breeze for you guys in the future because you have gone through it today and it's been absolutely awesome. Your questions are absolutely awesome. And on the chat, I can see that you guys are helping each other, which is so great to see because it means that you guys are actually understanding what you're doing. And there was some great discussion also about linear programming. So it's actually very refreshing to see that you guys are enjoying it. And on this sunny day, I hope that you guys are taking in all that you need to take in because it is so important for you guys to understand this part of your sections in your school because obviously they help you create greater marks for yourself. Over to you, Iti.
Thanks, Kato. I think you had a question.
Yes.
One of the learners had a question there.
Yes, it's a question by Dineo. Dineo asks, how do we determine which side is greater than or less than if our gradient happens to be a negative value?
Happens to be a negative value.
Yes.
All right. So if your gradient is negative, you should know. Okay, let me just illustrate something quickly here. If I remind you, in trigonometry, we did the ratios, and tan is one of the ratios that corresponds to how you find the gradient. What am I saying? If you have, we say our slope is y2 minus y1 over x2 minus x1, and we said that is the same as tan of the inclination of a line. Now ask yourself, where do we have tan negative? Then I'll remind you of what you call all students take coffee. Some people prefer to call it cast. Tan is positive in the first quadrant and the second quadrant. If a line is going to be to have a negative slope, then it suggests that you are in that area, in the second and the third quadrant. So every time you have a negative slope, it corresponds with a negative tan ratio. So it will go into the second quadrant. Now, really, if you ask me, when do you tell when it's negative? Basically, that's the answer. It must go into the second quadrant. I think that answers your question. And if you're not satisfied, you can actually post a follow-up question on that.
That would be great, yes.
All right. Right. Let's proceed with some more examples, maybe. And one thing you must notice is most of our constraints will have negative slope. Will have negative slope. They will all be slanting toward the left. Okay. And you can have constraints that have positive slope, for instance, where the information is given in the form of the ratio between your variables, for instance. So that tends to come out as a positive slope. Okay. So let's proceed and do two more examples, and I hope that will settle it today. Let's see. If we now have two more objective functions, this one, the R I've chosen to represent revenue. Revenue. And your revenue, you want to maximize it. Okay. In business, you want it to be the highest. So you want to maximize revenue given the revenue function. And for the Q, I'm suggesting that a quantity that you want to accommodate. Quantity accommodated, like I said, in the hotel or something, or in a restaurant. So you want to maximize that as well. All right. So early on, okay, now notice that the objective functions that I gave you 4 of them. One was about cost, one was about profit, and then this one is quantity accommodated and revenue. So 3 of them you had to maximize. And I said, when you look at the objective function itself, your constant term represents your y-intercept. That y-intercept, as you increase it, you are going to the highest value. As you go lower, you are actually searching for, the minimum. For instance, in the case of cost, our graph would have been, our function would have been pulled downward until it touches the last vertex of your polygon. All right. So in this case, let's deal with this revenue. All right. So if we rearrange this equation, it will come out as 3y equals to minus x plus r. Okay. Then you divide both sides by 3, everything by 3. You end up with y equals to minus 1 over 3x plus r divided by 3. So that becomes the y-intercept that you want to optimize. And in this case, obviously, your y-intercept, as it increases, you get the highest revenue. It corresponds with the highest revenue. So the way we draw it here is, depending on how the slope is, you then draw it so that your revenue starts somewhere at the extreme side of your feasible region, carries on until the other extreme. Okay, so let's call this R1 and R2. Right, so you move in that direction to maximize. You move you translate your Sesh line upward if you're maximizing. Right, and it's not always going to be that it touches at that point, for instance. You could have a revenue function that has got a gentler slope. It's important, therefore, to say if you have a feasible region like that, let's go for a different pen here. Your slope, the slope of your objective function could be as gentle such that it touches this point. Let's call it A, B, C, D. It could be that gentle that it touches this first. But it could even be gentler than this, and you find yourself touching D first. Let's say your line was like that, of the objective function. So really depends on what the slope of your objective function is as to how you draw your sesh lines. Okay, if I show you the blue ones, then that would be running, you draw all the parallel lines until you touch the last one. So that's the direction you'd be moving to optimize your objective function. And for the other color, these lines would be running across the feasible region until you touch C as the last point. So as to which line, as to which point on the polygon you are going to cut last depends more on the slope of your objective function. You still targeting for the highest y-intercept for any sesh line that sesh lines that you're using. All right, if you're maximizing. All right, I was on this one. In this case, if we take, let's put a few values here. If we take values like, let's just pick a few values, a set of XY values that will give us the same revenue. Let's say we've got a set like 0, and what's that? That line will pass there. Let's say, 0 and 0. That's one of the values you can substitute into that equation. You could substitute, let's say, 1 and 3. And these values that you substitute is just for you to draw the sesh lines. And they will not, for instance, if we use the first one, it will be a line that passes through 0. It's nowhere near your feasible region. Therefore, it is not part of the solution at all. So you need to keep going on, picking the values that will be. In fact, the best is to look at to find the values at your vertices, and substitute them in there. You will see that your lines, there will be a set of coordinates that will satisfy. Let's see that. That will satisfy the feasible region, and that is what you'll be testing as you go along. If it's outside the feasible region, that value is not going to work as a combination or the best combination in the end. All right. I wonder if there's any question, because I'm about to wrap up.
Oh, okay. Let me just check right here for you. There was one. Someone asked, when we're looking, sorry, now I've just lost it. When using the search line, which equation do we use?
I was actually explaining that right now.
Yes.
I said your objective function. Your objective will either be to get the highest profit, or to get the lowest cost, or to accommodate as many people as you desire to, right? So that being your objective, we represent that as an equation which we draw several parallel lines across our feasible region. That's what you call the sesh line. And that sesh line, because the y-intercept of those lines keep changing, as you increase the y-intercept, because of the different profit lines, they are all parallel, you are basically optimizing in the positive direction. You are maximizing. The word optimize basically applies to minimizing or maximizing. Then if you go in the opposite direction, across your feasible region, you are actually minimizing, Right. So all you do is draw parallel lines
Okay.
across that.
Okay. Awesome. Thank you, E.T.
All right. I'm gonna remind our viewers out there that what is important is that you know how to convert information from one form to the other. If you are given graphical information, be able to reduce it to equations, for instance, or inequalities. If you are given a word statement, you must be able to produce equations. And, even from one, you can even do it 3 times. Convert it from word statements to equations or inequalities, then be able to draw graphs. So that's 3 steps, a 3-step change in information. So anytime when you are asked questions in linear programming and actually in any other topic, you will find that you are asked to convert information from one form to the other. And
Thank you,
we can wrap
E.T.
it today.
Thank you very much. Thank you, Mindsetters, for joining us today. It's been such an awesome show. Owen even asked if we can have an extra hour. Unfortunately, we can't have an extra hour, but this hour that we've had has been so fantastic. Thank you to you, Mindsetters, and thank you to Liberty as well. And there'll be more next week, exactly.
Yes.
So join us again next week for some more maths, or you can stay on for the Grade 12 show. From us here at Learn Extra, bye-bye, guys. Enjoy the rest of your evening.